Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from one of the greatest scientists of the 21st century, Albert Einstein. He says, "A calm and modest life brings more happiness than the pursuit of success combined with constant restlessness." A lot of us are pursuing to achieve success and with a restlessness, and therefore, we need to really take these words of Albert Einstein and lead a calm and modest life. Let us recall what we learned in the last lecture. In the last lecture, we discussed about various kinds of orbits that are being devised by scientists to put satellites and also the space craft and space station, and we discuss 5 of them, particularly Earth reference orbits, namely equator orbit, retrograde equatorial orbit, polar orbit, and also Molniya orbit and geostationary orbit. We also learned what are the differences between geostationary orbit and geosynchronous orbit, and towards the end we also derive a relationship how to evaluate or how to find out the altitude of the orbit from the Earth's surface or any other planet, as a matter of fact. And today we will be discussing about basically what is the requisite velocity to reach an orbit. And this is a very pertinent question we need to answer, because such that we can develop the rocket engine to provide this requisite velocity to the rocket vehicle. Let us consider a planet. It can be Earth, it can be any other planet, and here we want to have an orbit, and that satellite has to be revolving around this orbit with certain orbital velocity v naught. And keep in mind that this mass of the satellite is a very small mass we are using, and we are using for the planet is a capital M, that is mass of this planet. It can be Earth, it can be any other planet, and let us say this is having Rp, this is your radius of the planet, and this is your R, and this is your radius between the center of the planet and center of the satellite. And now we need to look at how much energy has to be used for taking a satellite from the surface of this planet to at certain radius in the orbit. So, if you look at, it has to overcome the gravitational pull of the planet, and to overcome this gravitational pull of this planet, we need to provide certain amount of energy, and that energy we can find out. The energy required to reach an orbit of radius r by overcoming gravitational pull can be determined as, that is E, that is the energy is E required, is equal to basically G m and m by r square into dr, and that is has to be integrated from r p to r. Keep in mind that G is basically your gravitational constant, and m is the mass of planet, and small is the mass of satellite or a space lab or any other or space probe or whatever it may be. And this is has to be taken from the surface of the planet to that. So, therefore, it is integrated over r p by r. You recall that G m m by r square is the gravitational force and d r is the change in the radius. So, if I will integrate this, I can take this G m and m as a constant because it is not changing, and that will be dr by r square is r p by r. If you look at that will be G m, and that will be minus 1 by r if you integrate that r p to r. So, therefore, energy becomes basically G m m 1 by basically r p minus 1 by r, and that is basically saying that the energy required for this satellite to overcome the gravitational pull and can be placed in certain orbit depends on the r p and r. Of course, the other things are remaining constant. And but however, to achieve certain orbital velocity of v naught, you need to provide certain more amount of energy. Therefore, the total energy required to acquire orbital velocity of v naught to be placed in orbit of radius r is given by E t is equal to E plus the kinetic energy of this satellite or the mass to be taken from the earth surface and placed in an orbit is m v naught square divided by 2. So, if you look at the E already we know, this is G m m 1 by r p minus 1 by r plus m and v naught. We know the orbital velocity v naught already we have derived, that is G m by r. Keep in mind that this r is as r is equal to r p plus h. If you look at this is your h, h is your altitude. So, therefore, you can write down here G m square. So, therefore, this will be 2 r. So, if I take this G m m common from these two terms, that I will get G, this is your capital M, G m m small m, then I will get 1 by r p minus 1 by r plus 1 by 2 r. So, therefore, I will get basically E t is equal to G capital M m 1 by r p minus 1 by 2 r. This is my equation 1, I can say. So, therefore, you can see the total energy is basically again depend on the r p and r, and for a particular mass of the planet and mass of the satellite. And keep in mind that because of this two total energy being imparted to the satellite or the spacecraft, then it will be attaining certain velocity. That means, it will be having certain kinetic energy, and because of certain velocity imparted to that. So, therefore, we can basically find out, considering this total energy to be available for the vehicle as a kinetic energy. So, we can say that kinetic energy of the vehicle is equal to, or the satellite will be equal to m v t square. This is the total velocity acquired by the satellite is equal to the total energy, that is E t is equal to G m m and 1 by r p minus 2 by r. This is your capital M. So, therefore, we can cancel it out, this mass here, and this is basically I can also write down this as V t square is equal to G m 2 G m and 2 r minus r p divided by 2 r and r p. So, these two will be cancel it out, and we will get basically the total velocity V t is equal to G m. This is by, if you look at, that is by r p, or I can say this is r, right, into root over of entire root over. This will be basically r p, and 2 r will be 2 r p plus 2 h minus r p. So, you could recognize that the orbital velocity is equal to G m by r. So, as we know, as V naught is basically G m by r, that is your orbital velocity. So, therefore, I can write down as V t is equal to V naught, this is square. So, therefore, we will get as r p plus h divided by r p. So, this is your expression for the total velocity. This is equation 2. So, you can see from here that the total velocity, this is your total velocity of the vehicle is proportional to the orbital velocity, and it depends on the altitude for a particular radius of planet. So, we will look at it, what is this terminal velocity is required, and also as we know that the satellite, as we know in the low earth orbit, if the satellite is placed on at 185 kilometer from the surface of the earth, it is considered to be stable. So, let us now evaluate the orbital velocity and the terminal velocity at altitude of 185 kilometer from the surface of earth. So, therefore, the orbital velocity you can find out, that is g m r earth, this is the radius of earth plus h, and h is your altitude. So, if I substitute the value g, we know this is 6.67 10 power to minus 11 into the mass of the earth, we know this is basically earth, you can write down, that is 5.97 into 10 power to the 24 divided by the radius of earth 6371 plus 185, and you will get something 769,489 meter per second, or it will be around something 7.67 approximately kilometer per second. So, similarly, we can find out by using equation 2, we can get total velocity is equal to V naught root over R p plus h divided by R p. Basically, it is not R p, you can say this is R e, and because we are considering the earth. And when you substitute these values, V naught is 7,694.89 root over of that 6371, this will be 2h, keep in mind this will be 2h. Into 185 divided by 6371, and you will get Vt is equal to 7915.18 meter per second. So, you can see that there is a difference between the orbital velocity and total velocity. In this case, as the altitude is only 185 kilometer, you will see that the orbital velocity is very closer to the total velocity, although the total velocity is little bit higher than the orbital velocity. And if you go below this altitude, the differences will be diminishing out. So, you can see that this velocity being plotted over the altitude in this plot in a logarithm way, like on the x axis. So, you can see that orbit total velocity, which is shown in the red color, whereas the dashed line is representing the orbital velocity, and maybe around 100 kilometers. So, it is almost remaining constant with as it is altitude is increasing, it is decreasing, or the differences is increasing. And interestingly, the orbital velocity decreases with altitude, and which is more prominent particularly at a higher altitude, and the total velocity increases along with the altitude, and the differences are much higher at high altitude. Although at high altitude the orbital velocity required in a particular altitude is much smaller, but the total velocity which is required quite high. For example, if you talk about 10,000 kilometer of altitude. So, you will find this is your V naught, which is a smaller, much smaller than the lower earth orbit, and whereas the total velocity is quite high. You may think that it is advantageous to have a higher altitude, particularly when you consider about the lower orbital velocity. But however, the total velocity imparted to the satellite or this thing will be much higher. Therefore, you will have to spend more amount of energy. That means, you need more propellant to be carried by the rocket engine. So, therefore, you will have to pay the penalty for that. However, if you go in the lower altitude, then the stability is problem, there will be several other problems which will be coming, which we had discussed earlier. Therefore, the little medium level orbit or the even low earth orbit around 2000 kilometers, 1600 kilometers being used. So, let us now look at the escape velocity. If you want to escape from the gravitational pull of a planet, it is very important to give certain kind of energy such that the gravitational pull of a planet can be overcome. So, therefore, rocket engine must provide the sufficient amount of energy to the vehicle such that it can escape the gravitational pull of the planet, and this velocity we call it as a escape velocity. And for this it is important that the kinetic energy of the moving body must be equal to the work required to overcome the gravitational pull. In order to determine the escape velocity, we will have to equate the kinetic energy of the moving object, that is your satellite, I can say, is equal to the potential energy due to gravitational pull. So, it is having a escape velocity of V s. So, this is half m V s square is equal to that is the it has to overcome the potential energy is equal to the potential energy due to gravitational pull, that is G capital M, that is the mass of the planet, into m r square d r, it has to be integrated over to r to infinity, because it has to go out of the planet gravitational pull. So, if I take this G, m and m as a constant and take out of this thing, and we will get basically r p to infinity and d r by r square. So, this will get G m m minus 1 by r to infinity. So, which is basically equal to G m m, and this is 1 by infinity to minus plus 1 by r. So, is equal to G capital M m by r. So, therefore, you can cancel it out and you will get the escape velocity V s is equal to root over 2 G m by r, and that is 2 G m by r p plus h. So, we state that basically it is the escape velocity will be dependent on the altitude, and if it is from the and it will be also dependent on the orbital velocity. Interestingly, if you look at this g m by r p by h, root over of that is nothing but therefore, we can write down V s is equal to root over 2 and V naught as V naught is equal to basically g m by r. So, this is your equation maybe 4 and this is equation 5. So, from the Earth surface we know very well that escape velocity is something 11.2 kilometer per second. That means, if you want to escape the gravitational pull of the earth, then you will have to impart around 11.2 kilometer per second to that vehicle such that it can go away from this. And let us look at how does this escape velocity changing with altitude. You can say it is almost remaining constant in the lower r altitudes, but as it increases it is decreasing very rapidly with the higher altitudes. And keep in mind that the altitude is plotted in a log note. That means, it will be easier to escape from the earth pole provided you place in certain altitude and then you impart certain velocity such that you can escape very easily, and that we will be discussing about how to go about it little later on. Thank you very much, and we will be discussing more about various what you call interplanetary transfer path in the next lecture. Thank you very much.